A supposed comet is catching the attention of some of the nation's most renowned scientists, as one Harvard professor is raising the theory this may actually be a piece of alien technology.
Three-eye atlas, a silver ribbon across the sky, a sudden green halo the size of the sun. Backyard observers leaning out into the night, telescopes tilted, phones buzzing, and a single burning question. What just cut through our solar system and made a beeline past Mars? It was July when telescopes first flagged it. A routine sweep and then a wobble in the numbers. The Atlas survey in Chile reported a single track. The track turned into an orbit. The orbit turned into a headline. On paper, the path read like an oversized comet on a one-way trip. Hyperbolic, unbound, not coming back. The basic facts were simple and sharp. Discovered July 1st, 2025, traveling roughly 130,000 miles an hour. That's about 58 kilometers every second. To put that in human terms, at that speed, you cross the Atlantic in under 2 minutes. It would swing past Mars in early October. It would swoop by perihelion near the end of October, then vanish outward again. Closest pass to Earth was never inside the orbit of danger. This was observation, not crisis. The mainstream view was immediate. Most planetary scientists read the spectra and the images and said, natural comet, a body covered in ices, a heart of frozen material from the deep cold between stars. When sunlight warmed it, ice sublimated, gas and dust escaped. A coma formed, a tail unfurled. Routine physics, stretched to extremes, and yet the data kept throwing odd notes. The coma brightened and held steady. The color shifted from a muted red to a vivid green. The usual chemical fingerprints weren't where they should be. The size estimates wobbled. Some teams measured a huge, almost Manhattan-sized object. Others argued for a nucleus only a few kilometers across, hidden in a vast cloud. Orbital fits left residuals, tiny deviations. Not huge, not obvious, subtle, enough to whisper doubt. We have to keep that doubt on the table. Science lives in the space between confident answers and persistent questions. So let's be careful. Present the mainstream explanation first. Then follow the trail of anomalies. Then ask what changes if the unlikely turns out true. At first glance, the comet behaved like a comet. Infrared spectroscopy from powerful space telescopes and ground observatories showed strong carbon dioxide signals. JWST reported CO2 dominating the coma, with a CO2 to water ratio unusually high, roughly 8 carbon dioxide molecules for every water molecule in the measured emissions. That's far more CO2 than most familiar comets. It suggested formation far from any star where CO2 could freeze and remain stable. It suggested an origin out in the cold dark. Mainstream view, a large interstellar comet rich in carbon dioxide, one spectroscopist told colleagues in terse, careful language. That interpretation fit the chemistry. It fit many aspects of the coma's changing brightness. It fit a natural object arriving from the galactic neighborhood. But numbers have texture. The object's brightness profile behaved oddly. Instead of throwing off spikes or dips as a tumbling nucleus exposed new active regions, its light curve rose and fell smoothly. No clear rotational modulation. No obvious jets piercing the coma and flaring as seasons passed across a spinning surface. The coma grew enormous, hundreds of thousands of kilometers wide, and glowed a spectral green that caught everyone's eye. Most green comets owe their color to diatomic carbon, the so-called swan bands. That's the default. But here, careful spectral dissections showed little or none of that C2 signature. Instead, the green peak lined up with the forbidden oxygen line at 577 angstroms. Atomic oxygen, liberated by the breakup of CO2 and water, can glow green under the right conditions. In this case, the coma seemed to be a CO2 factory, with sunlight and energetic electrons ripping molecules apart and freeing oxygen atoms. Those atoms emit a green photon as they relax. The result? A green halo made by chemistry. Unusual, not impossible. Yet, chemistry alone didn't answer everything. The object's path through the solar system read like choreography. Orbit reconstructions showed it threading in sequence, and in a handful of months, the orbital neighborhoods of Mars, Earth, Venus, and then on to Jupiter. Statisticians ran models and said such a four-planet alignment in a single interstellar passerby was vanishingly rare. One group put the chance at far less than 1 in 10,000. Another, after correcting for observational biases, still called it an outlier, a needle threaded in a haystack. That is what set the rumor mill alight. Coincidence can feel like design when the odds are tiny, and design is a strong word. Some researchers, cautious and measured, used a milder phrasing: the geometry is suggestive. A few voices stepped out and said plainly, it looks like a reconnaissance sweep. A route with less than 0.005% chance of happening by pure coincidence, reads a calculation that circulated in technical chats and preprints. Enter the provocative names. Avi Loeb, who earlier fueled debate over Oumuamua, suggested the pattern was worth treating as more than chance. He proposed the scenario many of us know from speculative fiction: a probe sweeping past, maximizing observational opportunities while minimizing the risk of capture. He didn't claim proof. He requested that colleagues take the geometry seriously and test whether or not non-natural explanations could be ruled out. That kind of statement ignited social feeds. Some researchers pushed back. They pointed to survey bias. Telescopes spend more time near the ecliptic. We are more likely to spot visitors that skim the planetary plane. Once you account for that, rare alignments look less impossible. Other teams examined the residuals in the orbit and urged caution. Measurement errors, imperfect astrometry, subtle non-gravitational forces from jets, all can nudge an orbit enough to make a planned path appear choreographed. So the debate narrowed to measurable questions. Is there measurable, unexplained, non-gravitational acceleration after accounting for outgassing? Do spectroscopic fingerprints show any metallic lines or alloys, the kind that might flag artificial surfaces? Do any images show solid reflective structures inconsistent with fractal dust and ice? On the first point, tiny residuals exist. Orbital fits from multiple observatories show slight deviations from a perfectly gravitational arc. They are at the limit of current measurement precision. Some teams find the deviations vanish if you include modest outgassing forces in realistic directions. Other teams say the residuals persist no matter how you model jets. The difference often comes down to assumptions: the size of the nucleus, the grain size of the dust, the anisotropy of jets, the phase function used for brightness and scattering. On the second, spectroscopy. So far, spectra show the familiar molecular fingerprints: carbon dioxide, water vapor in much smaller amounts, silicate features, and carbonaceous grains. Reflectivity measurements match bright icy grains rather than engineered alloys. No clear metal lines, no narrow, sharp reflectance peaks that scream paint or polished foil. The simplest reading, Rachel Stevenson of JPL told colleagues, is a comet. The coma's chemistry and the reflectance point to natural materials, she said. Practical, conservative, and anchored to data. And yet, imagination refuses to be quiet. If an engine were hiding beneath a coma, what would it take to reveal itself? In the most extreme speculation, a self-illuminating object or a nuclear-powered probe might produce systematic forces as it thrusts or radiates. That could show up as continuous non-gravitational acceleration. It could also produce thermal signatures inconsistent with passive sublimation. An engine would likely generate high-frequency signals or narrowband emissions. So far, radio surveys have reported nothing unusual. Thermal infrared data, after careful modeling, fit passive heating and outgassing at the levels inferred from observed mass loss. Let's put numbers on the table and sense their scale. The spike in brightness in early October, a 6-fold increase over 2 nights recorded by alert amateurs in Australia and then confirmed by professional telescopes, was dramatic. If that represented new material exposed on a rotating nucleus, you'd expect corresponding jets and spikes. What we saw instead was a swelling coma and a shift in color. Mass loss estimates, depending on assumptions, range widely. Some models suggest dust production in the order of a few to a few dozen kilograms per second. Others, using different grain size distributions, push the number higher. None of these figures are small for interstellar bodies. They are large enough to light up a coma half the diameter of the sun. Heat and force interplay here. When volatiles sublimate, molecules leave the surface at some speed. That outflow creates a tiny thrust. Think of exhausting steam turning a wheel. For comets, these tiny nudges add up. Thermal recoil from uneven heating and localized jets can change the trajectory in measurable ways. So the default assumption is that non-gravitational motion comes from physics we already understand. It's not sexy. It's messy. It's science. And yet some teams found that even after modeling jets, residuals remain. They argue that the magnitude of unexplained acceleration coupled with the smoothness of the light curve makes a purely natural explanation uncomfortable. We're not saying it's alien, one dynamicist told a small group, but it's worth testing every hypothesis. That's an important scientific stance. The extraordinary claim always demands the most thorough testing. Another puzzling feature is the anti-tail. Instead of trailing away from the sun, a bright stream points sunward. You can see it both in HST frames and in careful ground-based imaging. Projection effects can produce sunward tails when Earth crosses a comet's orbital plane. But for this object, the geometry doesn't fit that simple explanation. The models that match the data invoke slow, large dust grains launched sunward by anisotropic outgassing. Big grains move slowly. They resist radiation pressure. The result is a sunward arc that persists for weeks. Add to that the plasma environment and charged grains, and the coma becomes a laboratory of complex interactions. Mars was where the stakes became tangible. As Earth's view dimmed toward the sun in late October, Mars orbiters moved into position. From our vantage, the object's solar elongation shrank. On or about October 21st, Earth-based telescopes started losing the practical ability to observe the comet. That meant handing the baton to robotic eyes around Mars. MRO's high-resolution imagers, ESA's Mars Express stereo cameras, the Trace Gas Orbiter's spectrometers, and MAVEN's ultraviolet and plasma instruments. Suddenly, Mars became not a passive planet, but an observatory. That handoff was a strategic pivot. If any spacecraft could take long-range snapshots, spectra, or even plasma measurements, it would be those orbiters. Teams reprogrammed observation plans. They negotiated precious windows. They worried about saturation, about tracking a fast target, about the sun creeping into fields of view. High-stakes troubleshooting replaced routine science schedules. The scramble reminded everyone of how fragile opportunity can be when a visitor rushes through on a one-way ticket. Why did that matter? Because the Mars flyby offered a chance at different kinds of data. Parallax from a distant spacecraft could refine the orbit. Plasma instruments could sample how the solar wind interacts with the coma. UV spectrometers could test for atomic oxygen and other emissions at ranges Earth telescopes could not. Radar-style imaging at long range might constrain nucleus size. These were the tools needed to turn suspicion into measurement, or to close the door on exotic ideas. And then the blackout. As perihelion approached around October 29th or 30th, the comet fell into the sun's glare from Earth's point of view. For weeks, the most dramatic chapter of its evolution would play out mainly out of sight. That pause in observation is a storyteller's nightmare and a scientist's stress test. It is precisely in those quiet intervals that theories are forged and alliances built. One camp predicted a smooth post-perihelion fade. Another warned of fragmentation, sudden breakage under solar stress. A third described an energetic flare, a last gasp of buried volatiles exposed by cracking. Each outcome would carry a distinctive spectral and photometric signature. None were guaranteed. History keeps a quiet ledger. We remember Oumuamua and Boris. Each visitor taught us humility. Oumuamua arrived in 2017 as a strange, elongated, non-outgassing puzzle. Its unusual acceleration prompted exotic explanations and intense debate. Boris, arriving later, behaved more like a textbook comet with clear outgassing. Each taught a lesson. Our prior models are incomplete, and nature can deliver surprises. 3i Atlas now joined that short list, but bigger and louder in some ways. What would change if the unlikely turned out to be true, that this was an engineered object? The stakes would be off the charts. Not only would we have to confront the presence of an artifact from beyond our system, but we would need a global, legal, and ethical framework for response. Thankfully, the international community had already been nudged awake by planetary defense exercises. The Outer Space Treaty limits unilateral actions. United Nations committees and scientific bodies already discussed protocols for detection, observation, and cautious response. The default recommended stance was observe, consult, and prepare. That's the sensible path. Whether natural or not, hasty action would create more problems than it solved. Engineers ran what-ifs. Project Lyra-style intercepts remain technologically challenging. Pushing a spacecraft to match a fast interstellar trajectory demands delta-v beyond current launch capabilities. Light sail concepts could, in theory, reach extreme velocities, but only with years of preparation and massive infrastructure. For now, telescopes, Earth and space-based, remain our best instruments. There is a social and human element too. The rumor mill spins quickly around any hint of the extraordinary. Social platforms glom onto speculative lines from a few papers or a single scientist's tweet. That drives public expectations and sometimes prompts premature narratives. Responsible scientists try to correct misleading claims quickly, but uncertainty thrives in a vacuum. The blackout period made that vacuum noisy. Without new data, speculative models expanded to fill the gaps. So, what should a viewer take away right now? First, 3i Atlas is real. It's interstellar. It's extraordinary in certain metrics: chemistry, color, geometry. Second, the mainstream evidence-based reading remains a natural comet rich in carbon dioxide. That reading is supported by spectra, by reflectivity measurements, and by plausible dynamical models incorporating outgassing. Third, anomalies persist, small orbital residuals, an oddly consistent brightness profile, a rare path through 4 planetary neighborhoods. Those anomalies justify further observation and careful modeling. They do not, by themselves, prove engineered origin. Now let's walk through possible scenarios crisply and plainly. Scenario 1, natural comet pushed to extremes. The nucleus is porous and rich in CO2. Sunlight begins to sublimate deeply buried volatiles. Large grains are launched in anisotropic jets. The coma grows immense. Non-gravitational accelerations appear because those jets produce tiny but measurable thrust. Spectra show CO2 dominance, OI green emission, and silicate dust. Mars orbiters catch a broad, dusty halo. Perihelion stresses the nucleus, perhaps leading to fragmentation days or weeks later. We learn more about how interstellar ices survive long, cold voyages. Scenario 2, natural comet with unusual structure. Here the nucleus has unexpected mechanical properties, internal layering or massive voids. Those structural quirks cause unusual brightness stability and jet patterns. The path that looks choreographed is actually a statistical outlier magnified by observational bias. Parallax and plasma data from Mars show nothing exotic. The antitail and green coma are explained by grain physics and CO2 chemistry. This version is unsettling because it forces revision in models, but it remains firmly natural. Scenario 3, quasi-engineered or hybrid object. Imagine a largely natural body with rare features, pockets of refractory, reflective material, or an internal heater from natural radioactive decay or chemical energy. That could alter outgassing patterns and cause unique spectral features. It's an edge case, it's harder to exclude and harder to prove. It would spark intense follow-up and perhaps a search for narrowband radio signals or unusual thermal anomalies. Scenario 4, artificial probe, the most sensational. If true, we would expect measurable directed forces unaccounted for by outgassing, thermal emission inconsistent with passive heating, or spectral lines from metallic surfaces. We might detect radio beacons or narrowband transmissions. We might find engineered geometry in resolved images. Right now, we have none of those hallmarks. No radio beacon, no shining metal cupola in images, no thermal excess inconsistent with sublimation. So while the probe hypothesis fuels headlines, the evidence remains thin. What would we do if the probe hypothesis gained weight? First, formal international coordination. Scientific data shared openly, multilateral policy consultation. Second, safety protocols. No deliberate signaling unless consensus emerges. Third, careful measurement campaigns. Maximize remote sensing, exploit every available spacecraft, and consider whether an intercept is feasible. Remember, even a decades-long mission would be a major human and technical undertaking. There is another twist to consider. Sometimes the most instructive findings are the humble, incremental ones. If 3i Atlas is a carbon dioxide monster, we learn about star-forming regions where CO2 freezes out, about the way ices mix and survive interstellar journeys. We learn about grain sizes and plasma interactions in massive comae. We refine models of non-gravitational motion and improve our orbit-fitting techniques. That's progress. It's not a cinematic reveal of aliens, but it's the slow, steady accumulation of knowledge that builds a foundation for future surprises. We also learn about our own readiness. The scramble to retask Mars orbiters shows how flexible modern missions can be. The blackout highlighted the fragility of Earth-based campaigns when geometry works against us, and it showed the value of having instruments in different places with different vantage points. These are the human moments behind the equations. Operators juggling schedules, engineers patching tracking algorithms, graduate students staying up late to reduce spectra, and amateur observers sending early alerts that turned into professional campaigns. Science is a collective effort, 1,000 small acts stitched together into a clearer picture. The instruments themselves deserve a line of praise. Think of JWST as a giant, exquisitely sensitive nose that can sniff faint molecular aromas in the infrared. Think of Hubble as a sharp-eyed portraitist, catching shape and subtle contrast. Ground observatories like Gemini, VLT, and WARLAB act as a global chorus, each adding a voice through different filters. Mars orbiters add a third vantage, like moving cameras in a stadium, giving parallax and timing that Earth alone cannot. That multi-instrument choreography is what turns a fleeting detection into a science campaign. Behind every spectrum and orbit fit are pipelines and protocols that rarely make headlines. Automated surveys scan terabytes, flagging moving dots. Human teams vet those flags, connect follow-up telescopes, and refine astrometry. That chain, from backyard observer to formal alert, can take hours. Sometimes a vigilant amateur provides the first hint that turns into a major campaign. The social network of observers is a scientific asset, rapid, distributed, humble, and crucial. Let's talk briefly about energy and scale in plain language. When astronomers estimate mass loss and dust production, they are measuring tiny grains in gas that, in aggregate, represent enormous surface areas. A handful of kilograms per second seems small until you imagine that over weeks it builds a coma that spans hundreds of thousands of kilometers. Comparing kinetic energy, 3I Atlas moving at tens of kilometers per second carries vast momentum. Yet compared to engineered craft, it is still a passive wanderer shaped by cold chemistry and sunlight. Another practical point, parallax from Mars orbiters does more than refine a number. It can reveal whether residuals are real or artifacts. Two observatories separated by tens of millions of kilometers see the object against slightly different star fields. That tiny shift, measured accurately, reduces uncertainties in orbit fits and in derived non-gravitational terms. In other words, Mars-based observations are the statistical tiebreaker for several competing models. There are also finer diagnostic tools that rarely get explained. Plasma instruments can detect how the solar wind is deflected by the coma. UV spectrometers check for atomic oxygen emissions and help measure the density and excitation states of gases. Infrared spectrometers reveal thermal fingerprints that tell us whether heat comes from passive warming or active energy sources. Combined, these instruments make a forensic kit for distant visitors. Finally, the human story threads throughout. Graduate students who cut their teeth on this event will carry techniques into future careers. Engineers who scrambled software patches learned how to make instruments more flexible. Public outreach teams learned how to translate caution into accessible explanations. That network of growth is a side effect of every cosmic surprise. We don't just gain data, we gain capability and experience. These extra elements, instrument roles, data pipelines, parallax leverage, diagnostic instruments, and human capacity building, are the quiet infrastructure behind any headline-grabbing moment. They turn speculation into testable models and rumor into disciplined inquiry. They also ensure that when the next visitor arrives, the global system is a little faster, a little wiser, and a bit more ready to answer the great, stubborn questions the universe keeps sending our way. So what happens next? The critical windows were marked. Mars flyby on October 3rd, perihelion around October 29 to 30, and a blackout of Earth-based views that lasted for weeks. After perihelion, when geometry allowed, telescopes would resume coverage. The months that followed would reveal whether the nucleus faded, flared, or fragmented. Mars orbiter data, when released, would be checked, rechecked, and reanalyzed. Every model would be updated. The debate would either narrow toward a comfortable natural explanation or widen into a more uncomfortable space. For now, here is one honest assessment. 3I Atlas is among the rarest and most informative visitors we have ever seen. It is a live experiment. It asks questions about interstellar chemistry, about comet mechanics, about how we observe and how we coordinate. It invites curiosity and demands rigor. It is both a marvel and a test of our methods. We should be bold enough to consider all possibilities and disciplined enough to follow the data. That's the scientific oath in a sentence. The unlikely deserves testing. The extraordinary deserves extraordinary data. The speculation is useful so long as it leads to measurable predictions that can be checked. In the quiet after the discovery, people asked what to watch for. Did the coma keep its green color? Did the light curve spike or fragment? Did Mars orbiters show any compact nucleus or unexpected thermal emission? Did plasma instruments record interactions outside the norm? Did radio surveys detect structured signals? Each yes or no nudges us closer to the truth. And for the public, one practical reassurance: there is no impact danger. The object's path keeps it well away from Earth. The stakes are intellectual, not existential. We are not facing a collision, we are facing a puzzle. As the solar system turns and the science teams publish their careful papers, the greatest scene is still unfolding. Telescopes, both human and robotic, will continue to peel back layers. New data will refine or refute models. In the best case outcome, we return to our daily lives a bit wiser. Better models, better instruments, and a sharper sense of how to react when the universe hands us a puzzle. So here's the provocative question that closes this chapter and opens the next. Did an interstellar visitor simply follow the rules of physics, pushed to extremes by chemistry and structure? Or did we, for the first time, glimpse an object that carries signs of intent, a reconnaissance sweep designed to see and not be caught? Only evidence will answer. For now, 3i Atlas sits at the edge of our knowledge like a light on the horizon. It forces us to choose patience over panic, measurement over rumor, and curiosity over fear. In months and years to come, we will look back at the data and know whether we were watching a comet shaped by strange chemistry, or a messenger whose maker chose a path through 4 planetary neighborhoods to learn what we might do. Either way, this visitor has done what true science loves. It has surprised us. It has made us think harder about how small ice, starlight, and chance can combine to make something that looks almost deliberate. It has also reminded us of a deeper truth. Our tools are improving. Our networks are faster. Our willingness to coordinate is real. And when the next strange visitor arrives, as surely it will, we will be better prepared, more skeptical of easy answers, and more ready to listen. For now, keep watching the skies, but watch with a scientist's eye. Read the data, not the headlines. Celebrate the wonder, but let evidence guide your awe. The universe has handed us a riddle. We have the instruments to solve it. The final verdict will arrive not on rumor or fear, but in spectra, in trajectories, and in patient, careful analysis. And when that verdict comes, we will tell the story again, not as a rumor, but as a measured chapter in humanity's small, courageous history of paying attention to the quiet, fast visitors that sweep through our neighborhood from the dark between the stars. In that slow accumulation of skills, we win the true prize: better science and readiness.